In the last lecture, we have been working with the orbit determination problem. So, it is a part of the two body problem. So, in this lecture, we continue with that. The orbit determination problem, it has many sub parts. So, the last time what we did that given the initial position and the velocity, then we get the orbital elements, or vice versa if the orbital elements are given at certain instant of time. So, at that instant of time you find out the position and the velocity vectors of the satellite. So, but there are certainly other components into this orbit determination problem. So, we call this as the Kepler's equation. So, Kepler's equation basically it deals with the propagation of the true anomaly. So, under the assumption that the earth or any heavenly body is a spherical mass. So, the orbit of a satellite under such situations, a spherical and homogeneous mass. So, orbit of the orbit under such situation, it remains either an elliptical or the circular orbit. So, if it is like that, or it may be depending on the initial position and velocity, even parabolic or the hyperbolic, but the main thing is that there are no perturbative forces available at that time. So, considering only this two body problem. So, if the perturbative forces are there, then the orbital elements they change with time. So, here in our situation perturbative forces are not present, and therefore, only the true anomaly it changes with the time, means the position of the satellite in the orbit it changes with time, and that position is here we indicate in terms of the true anomaly, that is theta. Other parameters etc., like the semi major axis, angle of inclination, nodal angle, argument of Parisi and eccentricity, they all remain constant. So, under this assumption that all these 5 elements are remaining constant and only the true anomaly is changing with time. So, we work for the Kepler's equation, which is just projecting this, that the 5 elements remaining constant and then theta is varying. So, at the time t, how the at the present time if theta is known. So, how at the next time the theta will be given. So, this is part of our Kepler's equation, and thereafter we will go into the Kepler's problem. So, Kepler's problem it is related to the Kepler's equation, not much different, but little bit technically different. So, we will look into that afterwards, but we will not develop the Kepler's equation final in the full form, because that involves the propagation of the ephemeris completely, means the given the position and velocity of the satellite at time t 0, then find out the position and velocity of the satellite at any other time t, and there are different methods for that, and obviously one method is doing the numerical integration. So, we will avoid that because of the in this particular course all these details cannot be included. So, we go with the Kepler's equation. So, in the orbit determination problem till now what we have done. So, orbit determination problem, it can be divided into determination of orbital elements from the initial position r 0 and velocity v 0, or say r v at t. The second problem is the inverse of this. So, inverse of the above statement, that is given orbital elements find r v at t. The third is given r 0 v 0, find r b at t. So, this problem, this is especially referred to as the Kepler's problem, the third one, third statement here. Okay. So, under the third statement, we have two ways of finding r b at time t. First is to solve r double dot is equal to minus mu by r cube r by numerically integrating The second one is to find the elements and then compute r b at time t. This can be done both numerically and analytically. A subset of the above problem is to find the ephemeris. That is r and theta as a function of time. Now, given the equation, we know that r square theta dot, this is equal to h, this is a constant. Therefore, from here we can write r square by h d theta is equal to dt. We can integrate it between, say, the starting time t to t and the theta from 0 to theta, where the satellite at the perigee at theta is equal to 0. So, this is theta and the coordinate of this point is r theta. So, this point is the perigee point, So, we are measuring theta from this place, okay, and t is also being measured from this place. So, if we write this point as the capital T, or we can put a equally 0 here in this place if we count time from this place. So, find out solve this equation. So, this we can write as t minus t, this becomes, now L we know this r is nothing but L by 1 plus e cos theta. So, r square becomes this square and divided by h d theta 0 to theta. So, this implies t minus t, this will be equal to L square divided by h 0 to theta by 1 plus e cos theta whole square. Now, we know that mu times L, this is nothing but h square. So, this implies L square will be h to the power 4 by mu square. So, we can put here in this place h to the power 4 by mu square h times 0 to theta whole square. So, this is h cube divided by mu square 0 to theta d theta by 1 plus cos theta whole square. So, this is our equation number 1. Now, so or either we write here h cube by mu square 0 to theta d theta by 1 plus cos theta whole square. This is our equation number 1. So, solve this equation. So, solving this equation requires certain manipulation. So, we first solve it for the case where e is equal to 1. So, here we have missed out e cos theta, we put here e cos theta. Okay. So, we deal with the case 1 when e is equal to 1. So, this is e is equal to 1 is for standing for the parabolic orbit. So, for e is equal to 1, t minus t becomes h cube by mu square 0 to theta d theta by 1 plus cos theta whole square. Okay. And this is easy to solve this integration problem. Okay. T minus t h cube by mu square 0 to theta d theta by, now 1 plus cos theta, we can write this as 4 cos square theta by 2, 4 times cos square theta by 2. So, ultimately this will give h cube by 4 mu square 0 to theta d theta by cos square theta by 2. So, cos square theta by 2. So, this will become 4, because 1 plus cos theta is equal to 2 cos square theta by 2. So, therefore, this becomes 4 cos to the power 4 theta by 2, and here also we have to put cos to the power 4 theta by 2, because here we have 1 plus cos theta square. Okay. So, here this quantity will be 4. Now, changing cos to the power 4 theta to sec theta term. So, this is becoming sec to the power 4 theta by 2 d theta. So, this can be further written as 0 to theta 1 plus tan square theta times theta by 2 times sec square theta by 2 d theta. Now, this can be easily integrated. So, we break this into two terms, h q by this is 4 mu square, 4 we have taken outside. So, this is 4 mu square 0 to theta sec square theta by 2 d theta and plus tan square theta by 2 times sec square theta by 2 d theta. Now, these are broken into two simple integration terms, and therefore, it can be easily seen that this quantity can be written as sec square theta. This is nothing but if you take the tan term. So, this can be written as 2 tan theta by 2. So, we put here between 0 and theta and plus, if we differentiate, if we can check from here, if we have tan q theta by 2. So, if we differentiate that, so we get this term tan square theta by 2 times sec square theta by 2. So, from here we can write 2 by 3 tan to the power q theta by 2 between 0 and theta. So, we can check it, this will become 3 tan square theta by 2 times sec square theta by 2, and then differentiating theta by 2, this will give 1 by 2. So, if we use for that term, so 2 by 3 cancels out the 3 and 2. So, therefore, this 2 and 3 has appeared here, 2 by 3 has appeared. So, this implies t minus t, this is equal to h q by 4 mu square. Okay. So, from this equation, if we insert the this boundary values 0 and theta, so we get this as 2 tan theta by 2 plus 2 by 3 tan q theta by 2. S q by 4 mu square, and this will come 2 we cancel out. So, this is tan theta by 2 plus 1 by 3 tan to the power q theta by 2. This is our equation number 2. So, this equation gives the relation for the theta. So, if you know the time t, okay, so at that time t, what will be the value of theta can be calculated by solving this equation. Now, the case 2, when E is less than 1. So, this is the case of an ellipse. So, here we use certain results from our geometry. This is theta. Suppose this is the point P, and we extend this line above. This is the line perpendicular to the this axis. So, extend it and it meets the this point here. So, the inner one is an ellipse, this is an ellipse, and this is a circle. So, ellipse semi major axis is A and circle radius is also A. So, next we have the center of the circle here. Okay. So, we join this point from here to here. The angle theta here is true anomaly, okay. And this angle, this is indicated by capital E, and this angle is eccentric anomaly. Okay. This point we write as N, this is O, okay. This axis we write as X, and here this axis we indicate as Y. Okay. So, the distance from the focus to the perigee point of this ellipse, this is nothing but this quantity is from here to here, this is A times 1 minus E, A times 1 minus E. So, this is our perigee point. Let us say this is, here we write it as perigee here. The distance then from here to here, this will be A times C. This can be easily calculated. We can do the calculation here itself. We have, let us write this point as A and this point as B, then A B is nothing but A, okay. And O B is, we know this is A times 1 minus C, therefore, AO will be A B minus O B. So, A B is A minus and O B is A times 1 minus C. So, this cancels out and this leaves us with AE. So, this is the quantity we have shown here. Okay. Now, from here so, what we have done, we have 16, we have introduced a new variable slash element known as eccentric anomaly. So, new orbital element, this is orbital element. So, but one should remember that this is not an extra variable, this is not an extra element required to describe the orbit, okay. Because the orbit is described always by total 6 number of elements. Therefore, either we use the true anomaly or the eccentric anomaly, just now we have introduced, both will work, okay, because they are related together. So, here we have introduced a new orbital new variable slash element, the orbital element, okay, E, which is called the eccentric anomaly, and theta is our true anomaly. So, here we try to find out the relation between E and theta first, and moreover this can be done geometrically, but we will try to go here using the analytical method. So, the coordinate of point P is P x y, and this we can also write as P r theta. Or P r theta. So, now from our geometry you can look into your earlier higher geometry book. Okay, P n by m n, it can be written as B by A. Now, x is equal to, this is from geometry, of conic section. So, x becomes equal to r cos theta okay. And we can also express the same thing in terms of the eccentric anomaly. So, this can be written as A times cos E minus A E. Okay. Here this quantity is, this is the radius of the circle is nothing but A. So, the projection of this on this axis from here to here is A cos E, and from there then we are subtracting the quantity A E, which is the quantity from here to here, and therefore, we are getting O n. So, this quantity x is equal to r cos theta, this is nothing but O n. Okay. So, here basically what we have written, this is nothing but A n minus A o. Okay. So, x is equal to okay. Now, similarly we can little bit modify this, is make it compact, A times cos E minus E. So, this is our equation number 3. Similarly, y can be written as y is equal to r sin theta okay. This is the point P. So, and this is the quantity r okay. From here to here this vector is r, therefore, this is our y and this is x. So, y becomes r sin theta, So, this is nothing but P n sin theta, and we can use the relationship that we have just now written. So, we can use the relationship P n by m n is B by A. So, this is P n is equal to B by A times m n sin theta, and m n is the quantity here, which is you can see from here, this is the quantity from here to here, m n is nothing but A sin E. So, m n is A sin E. So, this A cancels out, this becomes B r sin theta is equal to this theta cancels, this is equal to P n. We do one correction here. Y is the quantity from here to here. So, this is r sin theta. So, we have written r sin theta here, and this is the quantity nothing but equal to P n. So, this is not P n sin theta, because r is not equal to P n. So, we delete this. So, this is B sin E. So, y is equal to B sin E. This is our equation number 4. Now, therefore, r square can be written as x square plus y square. So, from equation 3 and 4, we can write r square is equal to x square plus y square. So, x we have written as a times cos e minus e. So, this whole square and plus y square is b sin e, this whole square. So, you can reduce it to a square times 1 minus e cos e whole square. Where we can use this substitution, b square is equal to a square times 1 minus e square. Okay. So, from here we can write r square, let us expand it and write it. So, a square times cos e minus e whole square plus b square sin square e. So, this becomes a square times cos square e plus a square times e square minus 2 times a square cos e times c, and this can be written as a square. So, b square we can replace in terms of a square times 1 minus e square. So, this will become a square times sin square e minus a square times e square times sin square e. So, this term we can add. So, that will give us a square, here cos square e plus sin square e Okay. So, these two terms we have accounted for, and then we have a square e square taking common 1 minus sin square e, taking this term into account, and then we have the last term 2 a square cos square cos e, 2 a square e times cos e. So, this becomes a square plus a square e square cos square e minus 2 a square e cos e. So, can we write this as taking a square outside, 1 plus or 1 minus 2 e times cos e plus e square cos square a times this is small e square small e square cos square e. So, therefore, the quantity this becomes a square times 1 minus e cos e whole square. So, this implies r is equal to a times 1 minus e cos e. This is our equation number 5. Okay. So, once we have got the relationship between r and cos e, so next remains to find out the theta in terms of e. So, we can see from these two equations we have written earlier. Okay. So, cos theta we can write as equation number 3 we can look into. So, cos theta from equation number 3. So, this is page number 11.9. 11.10. So, from equation 3 cos theta can be written as a cos e minus e divided by r. Okay. So, this is nothing but a times cos e minus e, and r is equal to, we know from this place equation number 5, a times 1 minus e cos e. So, this is a times 1 minus e cos e. So, this substitution we have done for r, from this is from equation 5. So, thus we have cos theta is equal to cos e minus e divided by 1 minus e cos e. Okay. Now, doing little bit of manipulation. So, cos theta can be written as 1 minus tan square theta by 2 divided by 1 plus tan square theta by 2. Okay. Once we do this, so we can write now cos theta is equal to, this implies cos theta is equal to 1 minus tan square theta by 2. Okay. So, this is the quantity we get. Okay. Okay. Or we remove this, we first write now cos theta is equal to this quantity, and this equation, let us term this as equation number 6. Okay. And this is the equation number 7. From equation 6 and 7 we can write 1 minus tan square theta by 2 by 1 plus tan square theta by 2. This will be cos e minus e divided by 1 minus e cos e. This is our equation number 8. Now, applying componendo and dividendo to equation number 8. To equation 8, we can write this as 1 plus tan square theta by 2 plus, okay, or minus, let us write it minus. So, 1, so this becomes minus 1 minus tan square theta by 2 and 1 minus 1 plus tan square theta by 2 plus 1 minus tan square theta by 2. This becomes cos c minus c by 1 minus c cos c. So, this will give us 2 tan square theta by 2 divided by 2. So, we can cancel it out, and similarly on the right hand side also we have to apply componendo dividendo. So, here we are missing those terms. So, I will write it here. This will be 1 minus e cos e 1 minus e cos e minus this quantity and then this quantity and plus. So, we had in denominator this quantity. So, this quantity and plus cos e minus e. So, what we get on the right hand side. So, 1 minus e cos e and this we equate it. So, here we expand and write it 1 minus e cos e and this is minus cos e plus e and here this becomes 1 minus e cos e plus cos e minus e. So, the right hand side will become equal to 1 plus e minus 1 plus e cos e divided by 1 minus e and then if we take minus e from here. So, this will be 1 minus e cos e. So, this implies tan square theta by 2, this will be equal to 1 plus e times 1 minus cos e divided by the mixed terms here. This will be 1 plus 1 minus e and cos we are writing like this. So, cos e minus e cos e. So, this term is plus here. Okay. So, this becomes 1 plus cos e. Okay, and this term can be further simplified. So, this will become 1 plus e 1 minus e and this can be written as 2 sin square e by 2 divided by 2 cos square e by 2. So, this becomes 1 plus e by 1 minus e and tan square e by 2. So, this implies tan theta by 2, this is equal to 1 plus e by 1 minus e under root times tan e by 2. So, this is the relationship between the true anomaly and the eccentric anomaly, and the equation we number this as, this is equation number 9. Okay. So, here as theta increases from 0 to 2 pi 0 to pi. So, E also increases from 0 to pi and they coincide only at theta is equal to 0 and theta is equal to pi. Okay. So, once we have got this, so we have started with solving the equation for eccentricity lying between E is equal to 0 and 1. Okay. So, for solving this case, we need to go back into our original equation, okay, and then work out the whole thing. So, here what we require d theta, we need to replace d theta in terms of d. Therefore, we can write sec square theta by 2 times d theta, this will be equal to 1 plus e divided by 1 minus e under root times sec square e by 2, and this substitution we can e by 2 times d. So, this substitution we can do in our original equation. So, d theta can be further written as 1 plus e by 1 minus e under root times sec square e by 2 d divided by 1 plus tan square theta by 2. Okay, making further substitution, this equation can be simplified. So, this is our equation number 11, 12. Okay, so finally, we can write this as d theta is equal to 1 plus c by 1 minus c under root, and we need to, because we want to express everything in terms of eccentric anomaly, and therefore, we need to replace in the previous equation, in this equation, tan theta by 2 in terms of the here theta by 2 in terms of the eccentric anomaly. So, if we do this, so we have to make the substitution from equation number 9. So, substituting from equation 9. Okay. So, d theta can be written as 1 plus e divided by 1 minus e square root times 1 minus e cos square e by 2 plus 1 plus e sin square e by 2. Okay. So, after little simplification, we can write this as 1 minus e square under root divided by 1 minus e cos e d. Okay, this is very easy, we can reduce it to this quantity. Okay, so, this is our d theta. So, this is our equation number 10. Now, going back to our original equation, which is 0 to theta times r square divided by h d theta is equal to t to t dt is equal to t minus t. So, here we can replace r and d theta in terms of the r equation we have written in terms of eccentric anomaly, and d theta also just now we have expressed in terms of eccentric anomaly. So, if we do this substitution, we get a times 1 minus e cos e whole square divided by h, and d theta is 1 minus e square under root divided by 1 minus e cos e d, integrating it between. So, the limits changes from theta it becomes c, and on the right hand side this is t minus t. Okay. Or we can write t minus t, this is equal to a square times 1 minus e cos e whole square, and then 1 minus e square under root divided by h times 1 minus e cos e. Okay. So, this will cancel out here, giving us a square times 1 minus e cos e times 1 minus e square under root divided by h, put it between 0 and e, put it 0 and e, this is t d. Okay. So, little bit more simplification is we can do here, but here it is a very clear that this equation is, because a and e these are constant, h is constant, and therefore, the integrand it appears very simple here 1 minus e cos e times d, and we can integrate it and solve this equation. Okay. Therefore, this implies t minus t is equal to, you can take outside a square 1 minus e square under root divided by h 0 to e, and this becomes 1 minus e cos e times d. Okay. So, integrating, now this can be written as a times a 1 minus e square under root. So, this becomes b A b divided by h, and the integration of this will be e minus e sin e, okay, 0 to e. So, this is nothing but a b times e minus e sin e. Okay. So, this is the final equation we have got here, and this equation we write as equation number 11. Now, this equation can be simplified little bit more, and because we know here this term can be replaced in terms of the orbital period, mean orbital period. So, if we do that simplification, so we define one quantity what we call as the mean anomaly. So, we define another quantity, let us say we know the n or the angular rate average, this is the average, is nothing but mu to the power 1 by 2 divided by a to the power 3 by 2, and time period is therefore is given as 2 pi a to the power 3 by 2 times mu to the power 1 by 2. Already this has been proved. So, we have t minus t this we can write as a square times 1 minus e square, earlier we have derived this. So, times e minus e sin e. Okay. So, this we can further express as a cube by mu under root times e minus e sin e. Okay. So, how to get this? We will just look into this. So, a q by mu, this is nothing but quantity a q by mu, this is related to our quantity here that we have written earlier, the angular rate. So, this is just the inverse of this. So, this quantity can be written as 1 by n, where n is the average angular momentum. So, this is e minus e sin e. Okay. Therefore, we can write n times t minus t, this is equal to e minus e sin e, and this quantity n times t minus t, this is written as m. So, m is equal to n times t minus t, this is called mean anomaly. Okay. Thus, what we get the final equation in the form m is equal to e minus e sin e. Okay. Okay. So, what we need to just prove that a q by this is a square times 1 minus c square under root divided by h. This quantity is equal to proof a q by mu under root. So, it is a very easy to see here the LHS, the quantity is a square 1 minus c square under root divided by h. So, we know that h square is nothing but mu times L. Okay. Therefore, h will be mu times L under root, and L we have written as A times 1 minus E square. So, this quantity becomes equal to this. So, here we have LHS becomes A square times mu times A 1 minus E square under root A square this quantity becomes equal to A square times 1 minus E square under root divided by mu times A times 1 minus E square under root. Okay. Therefore, this becomes equal to A to the power 3 by 2, 1 minus E square cancel out, leaving out 1 to the power 2. So, the LHS this is equal to RHS. Okay. So, this completes our derivation for this. Okay. So, what we got ultimately, this was our equation n times t minus t, this is equal to m is equal to E times E minus sin E, okay, and this is what is called Kepler's equation. Okay. So, in the next lecture we will cover it little bit more about this, but as a whole this topic is complete. So, I will describe little bit in the next lecture about the Kepler's problem. Okay. Thank you very much.